This is lesson 34 in our Calculus 3 series, Taylor and Maclaurin series. In the last lesson, we saw some functions that could be represented by power series. And in this lesson, we want to answer the bigger question, which functions can be represented by power series and how do we find these power series? So let's start by supposing that we have a function f of x that can be represented by a power series. So f of x would be of this form, series a sub n x minus c to the nth power. So if we expand that series, it looks like this. And we're saying that f can be represented this way for some interval of convergence. Let's explore what this series must look like. If we plug in x equals c, we're going to get f of c is equal to, and all of these terms are going to be 0, so we're just going to get a naught on the right side. So f of c must equal a naught. So that tells us that the first coefficient, a naught, of our series must be f of c. Now let's take the derivative of this series. We know by the last lesson that we can take the derivative term by term. So f prime of x is equal to, the derivative of a naught is 0. Here we're going to have a1. Here we're going to have 2a2 x minus c to the first, and so on. And if we plug c into the derivative, what do we get? We have f prime of c is equal to a1, because the rest of these terms are equal to 0 at x equals c. So that tells us that a1 must be f prime of c. Now if we do this for the second derivative and the third derivative, we find that a2 must be f double prime of c over 2, and a3 is f triple prime of c over 3 factorial. So we see this 3 factorial come up here and we realize that this 2 should be represented as really 2 factorial. And in fact, finding the nth derivative of this series gives us that a sub n is equal to the nth derivative evaluated at c over n factorial. So our series looks like this. F of x is equal to f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial x minus c squared plus f triple prime of c over 3 factorial x minus c to the third, and so on. And we can write that like this in summation notation. So what we're saying is that if f has a power series, it must be of this form. And we call this form the Taylor series expansion of f at x equals c. And when c is equal to 0, in other words, when the Taylor series is centered at x equals 0, we call this a Maclaurin series expansion of f. So far we're saying that if f has a power series expansion, it must be the Taylor series expansion. But we still don't know under what circumstances does f have a power series expansion. In other words, when does this series actually converge to f of x? When is this guaranteed? So let's explore a little further. If this was true, if the series converged to f of x, then we're saying that the sequence of partial sums converges to f of x. So let's introduce some new notation. Capital T sub n is going to be the nth partial sum of this power series. So this is the nth degree Taylor polynomial for f of x. We said that the infinite series was called the Taylor series. Now we're taking a finite partial sum, so what we get is actually a polynomial, and this is the nth degree Taylor polynomial for f of x. Let's call the remainder of that series capital R sub n of x. This is the remainder term for the nth degree Taylor polynomial. In other words, it's the rest of the terms in this series, so we're starting with n plus 1 going to infinity. So if f is equal to its Taylor series, then f of x is equal to the nth degree Taylor polynomial plus the nth remainder term. And we said that the t sub n are the partial sums for the series. So if this series converges to f of x, then the limit as n goes to infinity of t sub n must be equal to f. So what does this say about the remainder term r sub n? R sub n is equal to f minus t sub n. And if we take the limit as n goes to infinity of this remainder term, that's taking the limit as n goes to infinity of f minus t sub n. Well, f doesn't change as n changes, so we can pull f out of the limit. And this is really just f minus limit as n goes to infinity of t sub n. But again, this is the sequence of partial sums for the series. So this limit is equal to f of x. So that tells us the limit as n goes to infinity of the remainder term is equal to 0. And this is equivalent to saying that the Taylor series converges to f of x. So we're a little bit closer to the answer. So we were asking under what circumstances does this Taylor series converge to f of x? And well, now we have a necessary and sufficient condition. When r sub n goes to 0 as n goes to infinity, we know the Taylor series converges to f. So how are we going to be able to check if this remainder term goes to 0? Well, we're going to use Taylor's formula. If f has n plus 1 derivatives on an interval I around x equals c, then for each x in I, there exists a z strictly between x and c such that the remainder term can be written this way. This is the n plus first derivative evaluated at z over n plus 1 factorial times x minus c to the n plus 1. Now remember, we defined r sub n to be the rest of the series. So by definition, r sub n is the series n goes from capital N plus 1 to infinity of these Taylor terms. But now Taylor's formula is saying that instead of having infinitely many terms here, we could actually represent the entire sum here by one term evaluating at a different point. Not evaluating at c, but evaluating at some z between x and c. So Taylor's formula is saying that r sub n can be represented by one term, looks like a Taylor series term with n plus 1, but it's not evaluating the derivative at x equals c. We're saying that there exists some z for which this is true. And I want you to keep in mind that z depends on x and on n. So now to answer our question, to see if the Taylor series actually converges to f of x, we look at r sub n as given by Taylor's formula and see if the limit as n goes to infinity is equal to 0. If so, then we know that our Taylor series converges to f of x, and we would go on to find the interval of convergence and go from there. If not, f of x cannot be represented by a power series. And before we take a look at our first example, let's take a look at this common limit that comes up when taking the limit of our remainder terms r sub n. Let's take a look at limit n goes to infinity x to the nth power over n factorial. And let's show that this limit is equal to 0. To do that, we're going to go kind of a roundabout way and take a look at the series given by these terms. If we use the ratio test, we'll find that this series converges for all x. That tells us the sequence of terms must go to 0. And therefore this limit is equal to 0. And again, this limit is going to be helpful in a lot of the computations involving the limit of r sub n. So let's take a look at f of x equals e to the x. Let's prove that f can be represented by a power series and find that series. So remember, to prove that f of x can be represented by a power series, we need to show that limit n goes to infinity r sub n of x is equal to 0 for all x in the interval of convergence of this Taylor series. So let's start by finding the Taylor series. And we'll do that centered at x equals 0, just to keep things simple. So for f of x equals e to the x, the nth derivative we know is always going to be e to the x. So centered at x equals 0 means we're going to evaluate this nth derivative at x equals 0. So we're going to have e to the 0, which is equal to 1 for all n. So all of the derivative evaluations we're going to have in our Taylor series, they're all going to be equal to 1. And our center is 0, so that tells us our series looks like this. So far we have a Taylor series for f of x equals e to the x. We haven't yet proved that this actually converges to e to the x for any x values. Let's first find the interval of convergence of this series. We're going to do that using the ratio test. We have this limit here is equal to 0 for all x, which tells us that for all x in the real line, we get convergence. So far we know that this series converges for all x values. We just haven't yet proved that it converges actually to e to the x. So to prove that, we need to show that the limit as n goes to infinity of r sub n is equal to 0. And we're going to use Taylor's formula to examine that limit. So by Taylor's formula, we know that we can write r sub n this way. This is an n plus first derivative evaluated at some value z between x and 0. Remember, between the x value for which we're evaluating and the center of the series. So that looks like this for this function. And we want to prove that this goes to 0 as n goes to infinity. But note that z depends on the x, but also could depend on n. So before we take n going to infinity, we have to get rid of this e to the z and replace it by something about x or by a constant or something not involving z. So if we know that z is between x and 0, let's consider the case that x is positive. So that means we have 0 less than z less than x. We have that e to the z is less than e to the x. So our remainder term, we can say, is less than e to the x, x to the n plus 1 over n plus 1 factorial. And then since x is positive, we know that our remainder term is greater than or equal to 0. And we also know that e to the x, x to the n plus 1 over n plus 1 factorial is going to go to 0 as n goes to infinity. And that uses the limit we talked about above. As n goes to infinity, x to the n plus 1 over n plus 1 factorial is going to go to 0. So this side goes to 0, and this is greater than or equal to 0. So by the squeeze theorem, we have a limit as n goes to infinity, Rn of x must equal 0. So now we know that for positive x values, the Taylor series converges to e to the x. Let's continue on to see when x is negative. If x is negative, then we have x less than z less than 0, because z has to be strictly between 0 and x. And this tells us that e to the z is less than e to the 0, which is 1. So our remainder term is then less or equal to x to the n plus 1 over n plus 1 factorial. Now in this case, since x is negative, we need to use absolute value to be able to apply the squeeze theorem. So we have absolute value of r sub n is greater than or equal to 0. It's also less or equal to absolute x to the n plus 1 over n plus 1 factorial, which goes to 0 as n goes to infinity. So now we have absolute value of r sub n squeezed between 0 and 0 as n goes to infinity, and by the squeeze theorem, that limit must be equal to 0. And so that tells us that the limit of the terms without absolute value is also equal to 0. So now we have that our Taylor series converges to f of x for x positive and for x negative. For x equal to 0, since 0 is the center of the series, this power series is just equal to one term, so of course it converges there as well. And it converges to e to the 0. So now we've completely answered the question. We showed that for all x values, the Taylor series for e to the x actually converges to e to the x. Now let's take a look at this a little bit more. Remember that this means that the sequence of partial sums for the series converge to f of x. So we're saying that the Taylor polynomials, as n goes to infinity, converge to f of x. So the Taylor polynomials in this case are the finite summations, n goes from 0 to capital N, x to the n over n factorial. Let's take a look at some of these Taylor polynomials as compared to the original function e to the x. Here we're looking at the 5th degree Taylor polynomial for e to the x, and we can see e to the x is in blue and the 5th degree Taylor polynomial is in red. The center of this series is x equals 0. That's where the curves are exactly the same. And you can see as we move away from x equals 0, we see more and more of a difference between the function and the Taylor polynomial. So this is the 5th degree Taylor polynomial. Here we have the 6th degree Taylor polynomial. We can see a little bit better agreement with the original function. Here's the 9th degree and the 10th degree Taylor polynomials as well. So we could see that the higher order polynomial we take, the better agreement we get with the original function. In the next lesson, we'll talk about using these Taylor polynomials to approximate the function. Let's take a look at another example. Prove that f of x equals cosine x has a power series expansion around x equal pi over 2 and find the series. So again, we're going to start by finding the series and its interval of convergence. The Taylor series is going to be the kth derivative evaluated at pi over 2 over k factorial times x minus pi over 2 to the kth power, and k going from 0 to infinity. And I'm using the index k here because we're going to be changing to n's in a minute, and I don't want to have confusing notation. So let's take a look at what these series terms look like. The 0th derivative is the original function, that's cosine x. So f prime is negative sine x, f double prime negative cosine x, f triple prime sine x, and then we repeat this pattern. So we're centering our series at pi over 2, which means we need to evaluate these derivatives at pi over 2. So cosine of pi over 2 is 0, negative sine of pi over 2 is negative 1, negative cosine pi over 2 is 0, and sine of pi over 2 is 1. So these are going to be the coefficients that we get, and then we repeat this pattern. So let's take a look at the first few terms of the series. When k is equal to 0, our coefficient is 0, so nothing shows up in our power series. When k is equal to 1, we get negative x minus pi over 2 to the first power over 1 factorial. When k is equal to 2, our coefficient is 0, so nothing shows up in our power series. When k is equal to 3, we get a 1 times x minus pi over 2 to the third over 3 factorial. We're here. And we continue on with this pattern so we can see that we're only getting the odd powers of x minus pi over 2. And with that, we have an alternating sign. In order to be able to write this in a nice summation form, we're going to change the index from k to n and write the powers that we're getting as 2n plus 1. That's how we want to represent all of our odd powers. So we're going to have x minus pi over 2 to the 2n plus 1 over 2n plus 1 factorial. And then what's happening with this alternating sign? We need negative 1 to the n plus 1 power. So this is how we're going to write our power series for cosine x centered at pi over 2. Now let's find the interval of convergence. So we use the ratio test. And like the problem before, we have our limit equal to 0 for all x, which says that we have convergence for all x in the real numbers. So now we know that the Taylor series converges for all x. We just haven't yet proved that it converges to cosine x. To prove it converges to cosine x, we need to show that the limit as n goes to infinity of r sub n is equal to 0 for all x. So we use Taylor's formula to write r sub n as the n plus first derivative evaluated at some point z multiplied by x minus pi over 2 to the n plus 1 over n plus 1 factorial. And we know this z lies between x and pi over 2. Now, since all the derivatives of cosine x are either going to be a positive or negative cosine or a positive or negative sine, we know that the absolute value of this term is going to be less or equal to 1. So we're going to look at the absolute value of the remainder term so that we can replace this using an inequality. We can replace that by a 1. So we know that 0 is less or equal to the absolute value of the remainder term, and that is less or equal to x minus pi over 2 in absolute value to the n plus 1 over n plus 1 factorial, and this we know goes to 0 as n goes to infinity. So by the squeeze theorem, we have that the limit as n goes to infinity of absolute Rn is equal to 0 for all x, and so we know that without the absolute value, those terms are still going to go to 0 for all x. So now we know that this series converges to cosine x for all x. So we can say this series is equal to cosine x. And again, this means the sequence of partial sums of the series converges to cosine x. And this is the t sub n of x, the Taylor polynomials. So we can again look at the original function versus its Taylor polynomials. This is the 5th degree Taylor polynomial for cosine x, centered at pi over 2. So notice pi over 2 is approximately 1.5, so that's around here. That's the center of our power series, and this is the 5th degree polynomial. And we can see that as we increase the degree of the polynomial, this is the 7th degree polynomial, we get agreement on a larger interval. In other words, if we were using the polynomial to make an approximation for the original function, we would be able to do that for a wider interval of x values around the center with a higher degree polynomial. Here we have the 9th degree polynomial and the 10th degree polynomial. And here is a table of some common Taylor and Maclaurin series. And with this, we'll end our lesson on Taylor and Maclaurin series.